Now, again, let's imagine that we have this huge two-dimensional array where the rows of the array represent trading days and the columns represent different stocks, and what we have for each cell is the closing price for the given stocks on the given trading days. It may make sense to use slices to select ranges of trading dates, but it may not really make sense to use slices to select stocks that you're interested in. Perhaps the columns representing the stocks are organized alphabetically by ticker. You're probably not going to be interested in doing an analysis of all the stocks whose tickers start with an A. You would instead be interested in doing an analysis of tech stocks or pharmaceutical stocks or bank stocks or something like this. You can use what are called Boolean indexes to get more general row by row or column by column selections based on true or false values rather than just row ranges or column ranges. For example, here we have A1 again on slide 42, and I'm going to create a list named B rows containing true, false, true. Okay, now I know that variable name looks like browse, but it's not browse. Trust me, it's B rows. And if I say A1 sub B rows, well, A1 sub something is going to be the row index of the row that I want, or the rows that I want. And if the index here is a list or some other sequence of Boolean values, then for each Boolean value of true, that will select a row, and for each Boolean value of false, that will not select a row. So the upshot is that I am selecting the sub-0 row and the sub-2 row. That is the first row and the last row, but not the middle row, and indeed, that is the result that I see. I have in this view of A1, this is a view, just as if I had done slices. In this view of A1, I have the first row and the last row, but not the middle row of A1. As I said, that is a view, so if I were to say A1 sub B rows times gets a minus 1, let's say, that is going to modify all of the items in the first row and the last row of A1 to be the negatives of what they were originally. So originally we had 0, 2, 4, 6, 8. Now we have 0, minus 2, minus 4, minus 6, minus 8. And similarly for the last row, we have the negatives of the original values when we looked at A1 up here. The middle row has not been affected. Okay, so that's how I can use a Boolean index to select certain rows and not others. Similarly, I can use my slice notation to say, all right, I want all of the rows, and then use a sequence of Boolean values. Here I'm manually typing in my list to indicate which columns I want. Okay, so in this notation, I want all rows. I'm using regular slice notation to indicate I want all rows. But I only want the first column, that is the sub-0 column, and the fourth, the sub-3 column. So I want to get this column, and I want to get this column, but not any of the other columns. And so this would be representative of selecting, let's say, Apple and Cisco, not Caterpillar, and not Bank of America or ExxonMobil. Okay, and so now I have all rows, but only 2 columns from each of those rows. Rather than manually determining ahead of time which rows I want to select or which columns I want to select with these true and false values, I can actually perform a Boolean test on every item within an ND array by using the equality, inequality, and relational operators that we already know. So here's my A1 two-dimensional ND array, if I ask a1 less than minus 5, this is going to give me back a Boolean ND array of the same shape as a1. That is, it's going to be 3 rows and 5 columns. And for each item in a1, if that item is less than minus 5, I'm going to get a true. Otherwise, I'm going to get a false. So a1 sub 0 sub 0 is not less than minus 5, so I get a false. Likewise, a1 sub 0 sub 2 is not less than minus 5. But minus 6 and minus 8 are less than minus 5, so I'm going to get true for each of those items. And similarly, I'll get true for the minus 9 and the minus 15 in the second row, and for the minus 15 and the minus 9 in the third row. So I have 6 trues in the ND array of Booleans that I get from that relational test. I can use that relational test directly as an index into A1. The effect here, when I say A1 sub A1 less than minus 5 gets 8, is that each of the items where the Boolean index is true is going to be changed from whatever its original value was to 8. And when I look at A1 now, I will see that I have 8s now in the first row where I used to have minus 6 and minus 8. I have 8s where I used to have minus 9 and minus 15 in the second row, and then 8s where I used to have minus 15 and minus 9 in the third row. So this works fine for individual equality, inequality, or relational tests. If you want to do some kind of logical combination of tests, that is, the value is less than 5 or the value is greater than 9, the value is even, and the value is greater than 20. You can combine these equality, inequality, and relational comparisons with the symbolic ampersand for and, vertical bar for or, caret symbol for exclusive or, and tilde for invert. Now, invert is a unary operator. It's not a binary operator. Basically, if you take true and invert it, you get false. Likewise, if you take false and invert it, you get true. Notice that these operator symbols have higher precedence than the equality, inequality, and relational operators, so you need to remember to use parentheses around them. This is annoying, but you'll get used to it if you do this a few times. Once again, I have A1. This time I've got 6 of the cells have been changed to 8. And if I ask for A1 greater than 5 and A1 less than 9, my idea here is to try to identify the items within this two-dimensional array that are between 6 and 8 inclusive. Okay, 6, 7, and 8 are the values that are greater than 5 and less than 9 when I'm dealing with integers. But unfortunately, I get yelled at here because the ampersand symbol has higher precedence than the greater than symbol or the less than symbol. So let me remember my parentheses and say A1 greater than 5 in parentheses and A1 less than 9 in parentheses. And now I will get a 3-row, 5-column Boolean index that will be true for each item that is strictly greater than 5 and less than 9, and false otherwise. All right, so now I have true for all the 8s. Okay, so here are the 6 8s that I had. I also have one more true here for this 7. Okay, so the 6 8s are all strictly greater than 5 and strictly less than 9, so I get true for those. And I also have this value 7 here in the sub 1, sub 3 slot, which is true. And so if I now say A1 sub, and I give this test here, I'm going to copy and paste, minus gets 5. Okay, so I'm subtracting 5 from all of these values that started out strictly greater than 5 and strictly less than 9. And what we'll see now is that my 8s have all turned into 3s. So I've got 6 8s that have turned into 3s, and I've got 1 7 that has turned into a 2. Okay, so on slide 47, it's these red cells, which were the cells that were selected with true, that have been modified. The third style of indexing into an empty array, in addition to slicing and Boolean indexes, is what is somewhat weirdly called fancy indexes. Fancy indexes was the original term for this. Nowadays, a lot of people call these integer indexes. Fancy is not a particularly descriptive term. Let's take a look at how these so-called fancy indexes work. And the first thing I'm going to do here is to set A1 back to the original 3x5 two-dimensional ND array that we started all these examples with. Okay, so I've typed in A1 all over again, and now I'm back to the A1 that I started all these examples with. So for fancy indexing, within the square brackets, we specify in another set of square brackets which particular rows or columns we want. Now, inside the square brackets, the rows are the first dimension, and then the columns are the second dimension. So by using square brackets to index within A1, and then using square bracket 2, 0 as a fancy index, what I'm saying is that I want to get row sub 2 first, followed by row sub 0 afterward. So this not only allows me to select certain rows, but also to change the order of those rows in my result. And in fact, I can create duplicates of rows. I can say A1 sub 2, 2, 2, 2. And this is going to give me a result in which I have row sub 2 4 times, and that's all that I have. So I get an ND array that has 4 copies of row sub 2 from A1. If I want to do fancy indexing on columns, I can select all rows using my slice, which is colon, and then I can select the particular columns that I want to see and the order that I want to see those in. So A1 sub colon, comma, and then I want to see column sub 3, sub 2, sub 1, sub 2. All right, so column sub 3 is going to be the 6, the 7, the minus 2. I'm going to get that first, then column sub 2, 4, 5, minus 3, then column sub 1, 2, 3, minus 4, and then column sub 2 a second time. So my result here is a 3x4 array obtained from A1 using so-called fancy indexes. Okay, so if I say A1, and then I give integer indexes as my first dimension, let's say 3, 2, 1, and I give either nothing or a colon as my index 3. Oh, of course, index 3 is out of bounds. There is no row sub 3. Sorry about that. Okay, so A1 sub 2, 1, 0. Sorry, A1 sub 2, 1, 0. This is going to give me the rows of A1 in reverse order. All right, so A1 has 0, 2, 4, 6, 8 first, minus 5, minus 4, etc. last, and here I have swapped the orders of those rows. If I wish, I can use a colon for columns to explicitly indicate that I want all columns, but that's really the default, so nothing changes there. On the other hand, if I want selected columns from all rows, I do have to specify the colon to indicate that I want all rows, and then followed by my fancy index. Let me say 432 here. Okay, so I got columns. Well, now A1 has gone off the top of the page. Here we go. Okay, so now I've got columns sub 4, sub 3, and sub 2 in that order from all the rows. If you use fancy indexes for both the row subscript and the column subscript, somewhat strangely, that ends up creating a one-dimensional ND array matching up these indexes pairwise. All right, so if I say A1 sub and then sub rows 0, 1, 0, and 2, comma, and then sub column 0, 4, 2, and 0, notice that there have to be exactly as many row indexes as there are column indexes, and these things get matched up in pairs. So what I'm going to get is a one-dimensional ND array containing item sub 0, 0, and item sub 1, 4, and then sub 0, 2, and finally sub 2, 0. So 0, 0 is going to be the 0. 1, 4 is going to be the 9. 0, 2 is going to be the 4. And 2, 0 is going to be the -5. And so I get 0, 9, 4, -5 in my one-dimensional resulting ND array. Okay, so those are the three different mechanisms of selecting subsets of the rows and columns within a two-dimensional ND array on which you want to do some kind of analysis. We have slices, we have Boolean indexes, and we have these so-called fancy or integer indexes. A couple of other very important facilities that Numpy provides are the random submodule, which provides a large number of pseudo-random number generators for many different probability distributions, as well as the ability to randomly shuffle values, permute values, and sample from values, and also the linear algebra facilities that Numpy provides. Random is a submodule within NP. If we say np.random.rand 2, 3, the rand function will generate pseudorandom numbers from a uniform distribution from 0 up to but not including 1. So these are float values in the half-open interval 0 up to but not including 1. 2, 3 here are the dimensions that I want this ND array of random numbers to have. And here we see that I do get a 2-row by 3-column ND array of pseudorandom numbers from the interval 0, 1. These pseudorandom numbers are full float 64 values with 16 digits after the decimal point, although by default, when you display an ND array, it only shows 8 digits after the decimal point. Let me create this variable A1 to refer to a 2 by 3 ND array of pseudorandom numbers from uniform 0, 1. Here's A1 displayed by default. If I say A1 sub 0, 0, that is an individual float 64 value, and I will see the full 16 digits of precision that Python displays for such a value. If you're not interested in that much precision, you can use the .round method to specify the number of digits that you want for the rounded values of the cells within an ND array. Here I have A1. If I say A1 gets A1.round3, now I have values that have all been rounded to 3 digits. So whereas I used to have 0.9456 and so on, now I have 0.946 for my sub-0 item. All right, so rand gives me a pseudorandom number from uniform 0, 1. Rand n gives me pseudorandom numbers from normal 0, 1, that is a standard normal with a mean of 0 and a standard deviation of 1. This time I'm creating a 3-row and 5-column ND array. If I stop there, each one of these pseudorandom values is stored out to 16 digits of precision, but perhaps I would rather have fewer digits of precision, so I could say something like .round3. Okay, so .rand gives me float values, float 64 values from uniform 0, 1. rand_n gives me pseudorandom values from a standard normal distribution. rand_int, on the other hand, gives me integer values from a uniform distribution where I have to specify the lowest value to be in this distribution and the value that's one too far. So if I say rand_int and then 0, 10, the values that will generate are actually between 0 and 9 inclusive. And they'll be uniformly distributed among those values from 0 to 9. As the shape that I want this ND array to have, I'm specifying 4 rows and 7 columns. Okay, so as I type that thing in, bear in mind that what I got when I wrote these notes is going to be different from what I get now. A couple of other useful facilities from the random submodule are shuffle, which enables you to shuffle the items within an existing ND array, and permutation, which allows you to get a copy of an existing ND array with the values in that array permuted. Now, shuffle does modify directly the ND array that you apply it to, whereas permutation gives you back a permuted copy and does not modify the original array. So let's say I have A1 as np.arange 10. So A1 is now referring to an ND array, one-dimensional, with values between 0 and 9. I'm going to make a copy of A1 named A2. When I display A2, I see that at this moment it's the same as A1. But if I now say np.random.shuffle A2, this does change the order of the items in A2. It does not change the order of the items in A1, though, because A2 is a copy of A1. If I say np.random.permutation of A1, this gives me back essentially a shuffled copy of A1 without changing A1. All right, so here is a permutation of A1, but A1 is unchanged. And each time I ask for a permutation, I get back another shuffled copy of A1 without A1 being changed. Given some collection of values stored in an ND array, I can sample from that ND array using the choice method. If I say np.random.choice A1, 5, this is going to give me back a sample of 5 items from A1 with replacement. That is, each time an item is sampled from A1, the next time I sample an item from A1, the probability is the same as it was before that I'll get the same value I just got. Hence, here in my test run that I just did, I get back 2 twice. Because getting back a 2 does not in any way affect the probability of getting back a 2. And in this case, I happen to have gotten 2 back twice. When I wrote these notes, I happened to get 7 twice. You can request a sample without replacement by adding a keyword argument, replace equals false. And that will guarantee that each choice that's made is going to be distinct from the choices that have previously been made. So currently, altogether, NumPy's random submodule provides 35 different functions for generating pseudorandom numbers from a huge number of distributions. We looked at the standard normal distribution, which was rand_n. More generally, we can ask for np.random.normal, and we can specify the mean and the standard deviation and the number of items that we want to get as arguments. Okay, and here, of course, you can't tell for certain at a glance, but it certainly appears that the mean of all these values is going to be somewhere around 10, as opposed to somewhere around 0 or somewhere around 20. And again, looking at these values, it's sort of plausible that the standard deviation might be 2. It's probably not as low as 1. It's probably not as high as 3. And I can also have pseudorandom number generators from binomial distributions, exponential distributions, Poisson distributions, and many, many, many others. Linear algebra capabilities in NumPy are quite extensive. For example, if you have two matrices, A and B of appropriate dimensions, represented in ND arrays, then you can compute the product AB with the NP dot function. Equivalently, you can specify A as the current ND array object and use dot to multiply A by B. The transpose of a given ND array is simply that array dot capital T. So NP dot of A dot TA is how you compute A transpose A. For example, if I say A4 gets NP dot random rand_n 1 3 round 3, I now have a vector of 3 random draws from a standard normal distribution. A4 dot capital T is the transpose of that. I can compute the inner product by saying NP dot A4 comma A4 dot T, or the outer product by computing A4 dot T comma A4. The linalg submodule of NumPy provides many additional linear algebra functions and capabilities. Let's import numpy.linalg as LA. Notice that you can import a submodule using an abbreviation. And now I'm going to create A6 as a 3x3 matrix drawn from a standard normal. Okay, so here is my A6. One of the facilities that the linalg submodule provides is inverses, so I can say la.inv A6, and that will get me the inverse of A6, assuming that the inverse exists. And of course, we would expect that A6 dot its own inverse should give us back the identity matrix. Now, in fact, because of floating point round-off, we don't quite get the identity matrix, but we get something that's very, very close. The diagonal elements are, at least to the precision displayed, equal to 1, and the off-diagonal elements are very small. So if I round off all of these values to 15 places, then all of these very small values will be rounded down to 0. Whoops, in my example in the notes, rounding to 15 places did give us ones on the diagonal and then zeros elsewhere. But here I've got one value that's still significantly different from 0, even rounded to 15 places. So let's try this again, rounding to 14 places. And this time we see that, yes, we do get a recognizable identity matrix. Now, since A6 is invertible, that implies that its determinant must be something other than 0. We can find out the determinant with the la.det method or function. All right, so the determinant of this matrix is 0.491 roughly. And in turn, if we try to solve an equation of the form ax equals b for some specific vector b, we know that we're going to get one unique solution. So let's create for ourselves this vector b. Let's create a vector just 1, 1, 1. And now I know that I can solve ax equals b, that is a6 x equals this vector b. The linalg submodule provides me a solve function that I can call, in which I give my matrix as the first argument and the right-hand side b as the second argument. And here we have our solution, that is the vector x. And of course, the value of x should be the same thing that I get if I multiply the inverse of a times b. So here I'm multiplying the inverse of a6 times b, and indeed I do get that value for x. Numpy has many, many other facilities as well. For example, it has a whole collection of vectorized mathematical operations that operate on entire arrays very efficiently. Square root, e to the x, log of x, etc. There are a bunch of statistical methods available in Numpy. We can also do sorting and set operations. We can also read from data files directly into ND arrays, or take an ND array and put that into an output file in various formats. So that is the conclusion of week 4. We looked a little deeper at function definitions, mentioned the docstring that you should be in the habit of putting just below the def line that gives the name of the function and its parameters. We distinguished between positional parameters versus keyword parameters, which are parameters that have default values. We saw the ideas of global and local variables, and we saw that each time any function is called, a brand new symbol table, that is a dictionary, for that particular function's local variables is automatically created. If your function intends to return a value, you should have a return statement. If you forget, or if you intentionally leave out the return statement, what the function will return is none by default. A function can call itself. This is called recursion. And the key things about recursion are that you'd better have a stopping condition so that the recursion doesn't try to run forever. And assuming that the stopping condition has not yet been reached, what you do is divide the problem into a simple part, which you typically are able to solve directly, and a harder part, which is in the same form as the original problem, except simpler, so that you can call the same function again recursively to solve that harder part. Finally, we introduced Numpy, which gives you a variety of facilities for creating and comparing and doing arithmetic as well as linear algebra kinds of operations with n-dimensional arrays. We looked at 3 different ways of obtaining subsets of ND arrays, namely slices involving the colon, Boolean index involving equality, inequality, relational, and logical operators, and then this weird thing called fancy indexing that allows you to select and reorder, if you wish, certain rows or certain columns of an ND array. Okay, so that's that.